So, thank you for the introduction. Thank you very much to the organizer for inviting me and giving me the opportunity to give a talk. And it is a talk on a universality theorem, which I proved many years ago, but it's not yet published. But I gave details of the proof in Berlin. So all details would take about 4 hours. So it's not too complicated. Okay, and one big difference to the universality which we had so far for the modular spaces is that I allow additional points, so I allow projections, and I want to describe exactly the given semi-algebraic set. So for example, for my combinatorial object, I have a projective base, and I say one point should be exactly like this. And I don't bother where the other points are. And the objects are polyhedral maps, which are just a generalization of triangulations of two-dimensional manifolds. So let's start with a basic definition. So what are my objects? Well, in general, of course, universality, what does it mean? You have a given semi-algebraic set, and the way I consider it is you want to have some kind of algorithm to translate it to in a combinatorial object, and then to a geometric object. So it's a question of encoding all the time. And I'm also consider the complexity. So what are my objects? Well, an abstract polyhedral complex is just some two-dimensional generalization of a triangulation in that I allow polygons, let's say, and how to describe them combinatorially? Well, it's just a dihedral ordering, ordered set of vertices. So this is a polygon. I don't take the account of the orientation. And then, of course, such an object carries a topology in the natural way, or even a metric if you want. And then, what is a partial map? Well, a partial map is something which is not yet two-manifold, but the neighborhood of a vertex should be a subset of two-dimensional space. So, for example, let's say I have this, and then maybe here, and it need not be connected. And so this would be an example of a partial map. And this would be no partial map. If I have, let's say, 3. Sorry?
It's not really manifold with boundaries.
No, it's much less. It's, yes. It can be extended to a manifold That's the point. It's something which is a subset of a manifold, of two manifolds. So that's the point. So this, for example, would not be allowed, or let's say if I have something around one vertex, I cannot have an additional edge. So it's not allowed. So it's not. Okay, that's a partial map, and a map is just if it is a manifold, and a map with boundary, if it is a manifold with boundary, okay, in graph. Clear. Okay, so these are my objects, and one simple example is a polyhedral map on the torus with 4 quadrangles. So I have the identification, the usual way of vertices with the same label. And what I want is embeddings. So no self-intersections are allowed. And I want all polygons to be realized as convex polygons. And I want convex polygons sharing an edge should not be coplanar. So that is what called a realization. So I think it's quite clear what it means. So in a more complicated way, well, the polyhedral realization consists of an injective mapping of the vertices into 3 space. So that would be a 3-dimensional realization such that all given polygons correspond to planar convex polygons and no self-intersections. So the relative interior should be disjoint. Relative interior of a polygon is just interior of the polygon in 2 space. The relative interior of an edge is just the edge without the endpoints. Relative interior of a point is the point itself. Okay? Interior inside the affine Hall. No, I have no metric whatsoever. Yes, so it's just for describing the topology in a natural way. So I don't, it has nothing to do with the metric, no. Okay, now, for my realization space, I do not want to factor out the projective group, but I just say I have 5 specific vertices which are mapped on a projective basis. So I have this set of vertices, I give them in a fixed order, then a polyhedral embedding is called standard if the first 5 vertices are mapped on the projective basis, and the realization space is the set of all polyhedral standard embeddings, considered, of course, as a point in a 3n-dimensional space. Okay, so that is the realization space. And I cannot say too much about the realization space itself. Well, except, of course, that it's semi-algebraic set. So what is a semi-algebraic set in our context? Well, it's just, as ordinary, a finite Boolean combination of sets of which you can get from polynomial equalities and inequalities, and the coefficient field shall be the real algebraic numbers. So that are the coefficients. And always I take this field of coefficients. And the realization space, of course, is an abstract polyhedral complex, is, of course, a semi-algebraic set, because you can, the property of convexity of faces and no self-intersections you can describe by polynomial equalities and inequalities. Okay. Now, of course, it is well known that if I allow additional vertices and take just the realization of the given vertices, the projection of a semi-algebraic set, again, is a semi-algebraic set. That's a well-known theorem. Now I can state the main theorem. It is a universality theorem. And I state it in this way because it's context. So you give me a semi-algebraic set in 3n dimensions. I produce algorithmically a polyhedral map on some manifold, some 2 manifold or some genus, with 5 vertices for projective base, plus n vertices, which describe the semi-algebraic set, plus some additional vertices, such that the projection image of the realization space under the canonical projection just omit the other vertices, just consider the n vertices, is equal to your given set. Of course, the diagonal cannot occur because the mappings are injective. So no 2 vertices can coincide. So that is the mappings are mappings. You mean here, this? Yeah. Well, it is just I take the coordinates of the vertices, ignoring the first 5 vertices and ignoring the extra vertices. And just the coordinates, and it's given in a fixed order, so the vertices are labeled.
Why do you need k? Additional k?
Well, I need them for construction. I cannot say anything about. No, yes, one cannot really hope. One cannot really hope to describe the realization space itself. But of course, in some sense, it's a kind of extensions. So you can have the first 5 vertices and one vertex, and you say, well, this should have these algebraic numbers as coordinates exactly, and I don't care about where the other lie. And then I get a realization if and only if this vertex has these coordinates. Yes? No. Well, I don't care about the fibers. Yes, but quite clear that they are complicated. Quite clear. But there's, with these kind of objects and with embeddings, you cannot really hope for it. Because the topology can change if you, let's say, it looks like this or like that. You cannot expect really. That's a different question, of course, but you cannot really expect the fibers are simple. So it's a different spirit somehow, okay? A different aim somehow also. But what we get as easy corollaries, of course, are that if you have a strict subfield of the field of real algebraic numbers, you can construct a map which can be polyhedrally embedded in R3, but not in L3, okay? Because you just say one vertex has this algebraic number as coordinates. And of course, as a second corollary, because I want to say something about complexity of the construction, the realizability problem for maps in in maps in R3 is polynomial time equivalent to the existential theory of the reals. And that's it's NP hard. So it's as complicated as that. Okay. And one further remark. Well, it doesn't change really anything if you consider it in higher dimensions. You just take the projective base, of course, the appropriate projective space. So it does not really depend on dimension if it's at least 3. And yes, and one remark. The complexity is O of n. So the complexity of the construction is linear with the input of the semi-algebraic set. So of course, first I have to explain what is the input complexity of a semi-algebraic set. Okay. And I want to give you, let's say, the essence of the proof, and some steps I give full details and other steps just the general idea. Well, it's a question of encoding. So you give me the semi-algebraic sets. The first point is that I encode it by collinearities. So that is very similar to the one-stout construction, but one has to be careful. Then the second point is I encode the collinearities by a very special configuration which I construct. There I give full details. What is the miraculous object which encodes collinearities? Then from 1 and 2, I almost have a partial map. And then I consider universal extensions of partial maps to a map. So what is a universal extension? Well, universal extension means you have your partial map as a subset, and the extended map, which is a map, can be embedded if and only if the partial map has been embedded. So you can extend the embedding to embedding of the whole thing, no matter how do the first embedding. So that's universal extension, which is interesting in itself, I think. Okay, now we go to the steps of the proof. The first step is encoding the semi-algebraic set by collinearities. So this proposition. So you give me semi-algebraic set. Then I construct a set where I need additional vertices, W1 to Wn, and I take well, V1 to V5 are for the standard embeddings, okay? And W1 to Wn are those for the semi-algebraic set. But I need additional vertices. So superset of V in general, and a set of 3-element subsets, okay? And then the following is true. It exists in such a way that for each standard embedding of V to R3, so the projective base is fixed, following are equivalent. F can be extended to an injective mapping respecting all these given collinearities. I don't care about additional collinearities, it doesn't matter, for the additional vertices. And this is if and only if f of W1 to Wn is in my semi-algebraic set. So of course, if I formulated it as extensions, so of course, if two coordinates are equal, I don't have an embedding, but then it's not injective, the mapping in to begin with. Okay. And in addition, well, to get complexity bound, I would like also that each of the vertices is only used, let's say 4 times, it would be sufficient, 4 times in the set of 3-element sets. So it's not used too often. Okay? I don't care about the size of the U. It should be also O of n, but I do not care about multiplicative constants in complexity. Okay. So what are the steps for the first step? The steps for the proof of proposition 2, which is one of the simpler part of it, is first consider a normal form for the semi-algebraic set, which gives you the input complexity, the definition for input complexity. Second step is description that 3 lines meet in a point. Because I want to have injectivity. So I cannot say, well, there exists a point where they let me meet, because this is a point which has been used already, possibly. Okay? So I have to work with virtual points. So the whole proof is kind of virtual one start. So making heavy use of virtual points. Virtual point is just a description of a point. So if I want to describe this point, I say, well, it's the intersection of these 2 lines. So I say these 4 points describe this point. But I don't call this a point. But I can use it for further constructions, because I can describe the 3rd line goes through this point. So I use the point, but without saying that it's a point. Okay? So the idea is, I give a hint for the part of the construction. So it's a kind of von Staudt construction, but with virtual points. It's virtual points is not a definition, but it's informal. Okay? To give the idea.
Part of the data, but you use
Yes, I use, no, not even that they are not points which are in my set, because they may interfere with points which are given, of course. So that makes some difficulties in the detail. The first thing, I think, the first lemma should be some theorem which is well known, and it's very easy. It's kind of exercise in standard things from semi-algebraic sets. So I have my semi-algebraic set with my real algebraic coefficients, and I can put all the equalities and inequalities into just one polynomial equality with additional variables. Okay? So that should be quite clear. And if you have a reference, just after the talk. The second one is, now I have my one polynomial, and I want, with integer coefficients, I can build up it So I add many additional variables. And so my set can be represented this way. The 0 is the number 1, because I need the number 1. And then all expressions are, each expression has a new variable on the left-hand side and 2 old variables on the right-hand side, either addition or multiplication or minus. And the last equality, which is the important equality, is xn equals 1, okay? Equals 0, okay? Yes, I think that it should be. Yes, yes, I think that should be cut off. And this gives the complexity, and this number n is a complexity of my semi-algebraic set. So, for example, let's say 3. I have, what is the complexity? Just to give you a hint, well, I need 2 additions, so 2. Then I have a minus, well, it's plus and 1 minus. Then let's say I have something like through 3, it's nothing new because 3 I already know, I can use it again. And then I have 2 to the n for encoding integers. So, well, this I can do with n multiplications, okay? So this has complexity n. Then let's say times x. So I have 1 multiplication, 1 variable, then plus y, and then to the, let's say, 2 to the m. And so I have here 1, 1, and here I have m multiplication. So the complexity is just very small, okay? So it's quite efficient way of describing semi-algebraic sets. And this is my input complexity. And I consider the semi-algebraic set as given in this normal form. And now what I mean with virtual constructions. For example, I want to describe that 3 lines meet in a point. Well, first of all, well, I use this arcs, okay? But maybe the first thing I would like for this arc, this point, may be a point which I which cannot avoid something which I have. So maybe I need extra points on the same line. And then I use this arc, and then I get description of the virtual point. So this is kind of virtual construction. And then, for example, I need projections, of course. Well, I would like to have a cube for defining projections. Well, I cannot take the small cube from the projective base, but to take another cube. Because I have this vertex of a square, maybe some point, okay? I have to avoid points. So, okay. But that's not too difficult. Now comes the geometric encoding. So that was bunched out with virtual points. Well, geometric encoding. I have to encode the collinearities. So I have collinear points and nothing else, so to speak. Well, the first idea is that I take this, what I call a standard handle. It's just the triangular picture frame torus with one face removed. So the gray one quadrangle is removed, okay? So the triangular picture torus in realization, one removed. Then for each polyhedral embedding of H, if all 8 other quadrangles are strictly convex and planar, then the last one is also strictly convex and planar. This is very closely related to something which Zimutis did in a PhD thesis, so that's not very surprising. And also what I can do, of course, well, if you prescribe the convex quadrangle, all the rest can be done in a very small pyramid above this. Okay, so it's a very local construction. It's possible. Okay, and to prove this, I need, well, the planarity of the last quadrangle comes from projective geometry, and the convexity one just by elementary geometric considerations. If one quadrangle is non-convex, then 3 others are also non-convex, but the others I want it to be convex. So there exists also a non-convex version of that. But what is important in this innocent lemma is that neighboring faces are non-coplanar. Otherwise, it's wrong. Because consider a triangular picture frame with 3 quadrangles being coplanar. Then I take my picture frame, and then I have freedom to move one vertex, which keeps all other polygons planar except for one. And this would contradict it. So I need the neighboring faces are non-coplanar. This is which shows that it's important for the definition for my construction. Okay, so this is the first construction part. Quite simple. Now the second construction part, I put them together, is there exists a partial map K0 with 3 specific vertices x, y, z, such that for each injective mappings of these 3 vertices, it can be extended to a polyhedral embedding if and only if they're collinear. So this gives my encoding of the collinearities. Of course, what I want to have is, well, all polygons are quadrangles in this complex. And what I want, of course, is that it should not, the additional vertices should not cover really space, because they should not interfere. So I take an embedding of the K3 in 3 space, in an embedding, and I can do all of the construction arbitrarily close to this one-dimensional object. That is the point. Okay, now, and this is a kind of geometric main idea how to construct this. Well, proof of lemma 2. How do I get this complex? Well, this complex is K1. K0 is what I aim at, so this is intermediate step. K1 is composed from 8 standard handles. So this is a picture of 64 quadrangles, okay? And what I want is I just give you the quadrangles of the boundary, okay? So from the omitted faces, okay? So I have 8 quadrangles on the boundary. And I have written it here, what is the combinatorics of the 8 quadrangles. These are the vertices z, x, y, which I'm interested in. And then the 8 quadrangles appear in red quadrangles and blue quadrangles to see that this is realizable in 3 space. Namely, the red quadrangles, you have a pyramid going up, okay, and are contained in such a thing, and the blue ones going down. So the whole thing can be realized very close to this configuration. And it's also clear that you can, well, just push the configuration that it's close to 3 lines meeting in a point.
Use stereoscopic
Well, this is, well, and now the point is that this configuration of the boundary edges of the things which I started with is planar. So that's the point. How do you show that all vertices are coplanar? Well, I know, yeah? Yes. No, edges are red and blue.
I mean that you have a collection of quadrangles.
Yes.
And so if you take them as vertices and connect those that share diagonal adjacency in some sense, why do you take this complicated figure? Cannot you
Well, the point.
manage with, I think, with 4 quadrangles?
Well, the point is that I need these 3 special points. That's one point. And the second point is that I need the configuration to be very close to, possibly very close to the 3 lines. And I need the overlay, because I want to prove that it's coplanar, okay? And this means that what I need, well, why is the configuration coplanar? So I see 2 quadrangles from which I know that they are coplanar, convex. But they have to share a triangle which is not collinear. And this, yes, that's the point. I have to enforce that they are not collinear. No, yes. That's the point. These, and they share 3 vertices. So all 5 vertices are in the same plane. Okay, and then I continue. And so all vertices of this are in the same plane. So this is forced, if I realize it, polyhedralization of my 64 quadrangles. This part of the configuration is forced to be coplanar. Okay? And I get, well, and also because in my construction with collinearity, I have to ensure that it's possible, it needs enough flexibility to change the order of the 3 vertices. Okay? So otherwise, in an earlier version, I had a simpler one, but I needed the order of the vertices. So for any order of the vertices, same, it's possible to realize. Okay? So, okay. And now, this is, well, I know only that it's coplanar. Well, how we get collinearity? Well, that's quite simple. I just take 3 copies of this. And as I know that K33 is non-planar, at least 2 of the planes are different. So the 3 special vertices where the 3 configurations meet are collinear. So I have encoded collinearity without using much space. Okay? Okay, and now this is already, oh, sorry, more quickly than I thought. This is already, I'm very far with it. We begin with a set of W of vertices, which I constructed in the first step. So all these vertices. And encode the collinearities in which I have given with my lemma 2. Okay. And then the only thing which I want to add is some extra. I want it to be connected because it may be disconnected. So I need additional edges, but I cannot use the edge because I don't know where it passes through. So with 1 extra vertex. And now, if I put both things together, well, of course, the basic configuration one has to check that it's really a partial map. So I have one looks at it again, one sees 2 manifold vertices, and then I have some more manifold vertices, and it is orientable. And so if I put the 2 things together, I have an orientable partial map such that all polygons are quadrangles. And putting it together, I have shown theorem, the universality theorem, except for the property of being a map. Okay? Because it's very partial now. Okay. And
So where was the
Sorry?
Was start of the torus. You started with the torus
Yes.
with one hole.
Yes.
Where is it here in this construction? Was it already used?
Yes, yes, it was used very often. Oh, okay, I go back. Each of these quadrangles is only a symbol for handle. So yes. So this gives just the boundary configuration. So I have 64. Okay, this is a short version for 64 quadrangles. It's a configuration of 64 quadrangles. Yes, yes, I think it's clear now. Okay. Okay, okay, now, well, because such partial maps are not so nice objects, so we want to get really maps. I think universal extension is an interesting theme in itself. And let's say for general definition, I would not use this. It's just the things which I can do with this thing. Okay, so I added some properties which I can just get. So let's say I have an abstract polyhedral complex and a larger complex. Then I say the larger one is a universal extension if every polyhedral embedding of the smaller one can be extended to an embedding of the larger one. Okay. And also, this is some extra which I can get, is that the larger one can be embedded in epsilon neighborhood for any epsilon of the smaller one. And what I really want is that the additional vertices can be chosen in Q to the 3, because for my corollaries.
You mean the images?
The images, yes. Yes, the images of the vertices can be chosen. Okay. And, well, and the proposition is if I have a connected partial map, then there exists a universal extension to a map with boundary. That's the first part. If the original one has been orientable, then I have a universal extension to map with a boundary. And it can be chosen that all new polygons are triangles. Well, one should use it this way. Okay. And how is this done? With consideration of, so this is, okay, and putting these things together, I have proven a theorem. So this is, I think, the last slide which I should use. Okay, now, no, it's not finished. I have still some minutes. Not, and how does the universal extension work? Okay, and this I can do on the blackboard. Well, I have my partial map. Okay. And I also want to keep track of the O of n business of the complexity. So it should not be too complicated, this universal extension. And if you remember, in the first step, I said that new point, that a point occurs only in a few of these things. So what I get is that all of my complex, which I have constructed so far, I've bounded validity of the vertices. So it's bounded by a constant. And, well, universal extension. The problem is that for some vertices, the link may be not connected. So I want to connect it. And what I need is, this is just the neighborhood of one vertex. And here I have something, okay? Well, I put in triangles, enough triangles, and I already indicate how it will be realized later. So just in a very small neighborhood of these boundary edges, And what is the consequence? Well, the consequence, of course, is that if I have enough extra vertices here, it can be extended to embedding. And the second consequence is that the number of connected components drops by 1. Okay? And I do it as long so that I get not a manifold, but a manifold with boundary. So the number of components should be dropped to 1. Okay, and do this construction for the non-manifold. And what is the geometric problem? How many do I need? So this is an interesting question in its own right. And for the general thing, not only for the part of the proof, but as a theorem in itself, I consider the neighborhood of these vertices. It's on the sphere, and I have a spherical polygon and some isolated points. And what I want is, it's very similar to the planar thing. So I have a one-dimensional object, okay? And what would be a universal extension to a line. So I then they are labeled, and I want this topology, let's say. Okay? And no matter how these are embedded in the plane, I want that this extension, the number of vertices, is sufficient to go around it. And what I can do is, the exact number would be also an interesting question, of course. But what I can do is, if the number here is the same as the number of vertices altogether. And so for each thing, I have the number of vertices. So I have something like the number of vertices times the number of components. But in my construction of a universality theorem, I have a constant bound, so it doesn't matter. And here I have a quadratic bound somehow. Okay, that's the first point. And it gives rise to interesting geometric questions. Okay. Yes, yes. What is the exact number? Yes. And then the second part is, I have a map with boundary now. How do I get a universal extension to a map without boundary? Well, I take a doubling construction. So I have, let's say, this is maybe the boundary, and maybe it looks like this, and then I have maybe some manifold vertices. I just take this twice. I connect them with the boundary, and for the additional ones, of course, vertices connecting two boundary vertices, I have to subdivide in the new thing. I have to subdivide near the boundary of a vertex. I have to subdivide. But the manifold vertices make some difficulties, because manifold vertex is just a very complicated, the boundary is a very complicated closed spherical polygon. But I cannot use the vertex again. So what I get is some spherical polygon, which I want to triangulate universally. But that can be also done quadratically in the number of valence here. So it's a very completely explicit construction of this. Maybe I make a hole in here and take a universal triangulation of the polygon. Okay. And maybe, but how much time do you have? Still some minutes. Okay. So maybe, okay. 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 So I was more quick than I thought. But I have an exact construction for universal triangulation of a polygon. So, namely, the question is universal triangulation of convex polygons. Okay? And universal triangulation of a convex polygon. What does this mean? Well, it is well known and easy to see that if you have an embedding of a simple polygon, you can triangulate it without additional edges. And what I want is a universal triangulation with additional vertices such that for any triangulation I can get this. And I can classify. I have a polygon, okay? A definition. And I can consider any realization of the polygon as a simple polygon. And triangulation is universal, so this would, in a pentagon, one additional vertex. If for any embedding, I can use this combinatorial type with labeled vertices. Vertices are labeled, which can be geometrically realized. Okay, and so the theorem gives a complete classification of universal triangulations. Okay, the theorem states the following: three equivalent, the following equivalent. So I was not expecting a time, but it's an interesting thing also. It's not really needed for my other universality theorem, but it's different equivalent. First, let's say for n-gon. T is universal triangulation. In this sense, in the geometric sense, yeah? Okay? Triangulation of the n-gon. Second, it's a graph theoretic condition. The graph theoretic distance inside of the T is the same as a graph theoretic distance of the n-gon. So, no. Graph theoretic distance means number of edges in a path. So the graph theoretic distance in T is between two boundary vertices. Two vertices of the n-gon, and the n-gon is just the boundary of T is the same as on the boundary.
So it's not isolated.
Yes. And this is quite easy to see. Let's say one direction is quite easy to see because, well, why cannot I have short distance in the diagonal? Well, I just take these two vertices, and then I have many additional vertices. I can put it in a realization very close to this, and then I need this n-gon, this number of vertices. Okay, but I can go this way or that way, so the shorter of the two ways. No, it's a graph theoretic distance. It's just combinatorial. It's the number of edges, length of the path, number of.
But it isn't yet.
You can say it's a metric, yes, of course. Edges have length 1, and then induced metric, yes. And okay, and the third condition is, well, third condition is, which is a different kind of universality for any triangulation. So each triangulation of the n-gon which I call boundary of T, without additional vertices, of my vertices, is which I call strong minor. Of T. And strong minor means what I can do. I can shrink an edge to point, identify two vertices which are neighbors of one another, keeping the boundary. The boundary is fixed. So a strong minor would mean this is an interior edge, and then I just get this, okay? Identifying two, it's a surjective mapping from the graph, such that the pre-image is connected, okay? And edges are mapped to edges. Okay, and well, and it's not very difficult, but it's quite interesting. And what I have is a conjectural, well, and then of course with this you can say minimal universal triangulations with respect to edge shrinking. And then you can ask about the minimal number of vertices and the maximum number of vertices. And I have conjectured numbers and configurations for the lower and the upper bound, but I could not prove this exact number. It's quadratic. It's quadratic, and the lower bound is, well, the constant is n squared plus something, okay? A little bit, minus something. This is the number of additional vertices I need. About, and I have for my, this is a lower bound. No, it's an upper bound for lower bound. It's a configuration which I have and which I conjecture is the minimal one. And yes. Well, I think some quadratic universal, that has been done by some other authors. Okay? They have shown a lower bound, quadratic bound, and shown that quadratic is the best possible, but I have the exact numbers, conjectural, and the classification. What are the universal objects? And the upper bound is quite easy. It is for, let's say, for 2 n-gon, I have n minus squared additional vertices. I have a configuration with this. So this corresponds, of course, to n squared divided by 4. Okay? So these are the multiplicative constants. So that's, now I'm finished. So thank you very much for your attention.